I don't know. I think living is a transverse wall stress. We just apply 180 degree. Are we getting Brent with our walls? No, Brent's not allowed. We should remove the folks about Tom and all of the couches. I'm sorry, we're in an EO class. Yeah. We should remove the folks that put on all of the furniture and if Brent like brings anything that he can sleep on. We should remove it. So you guys just sleep on the floor with no covering. Yeah, we took the oh yeah, what were they named more? We will provide hospitality. You know, it's like those Kardashian beds in like parks. We should get we should replace our furniture with French blocks. I think what we can do, we don't have French blocks. All of the heavy sites French blocks. Yeah, he was a better electrical engineer than both of us combined. Therefore, having French blocks in furniture is twice better. And I think this is causation. Yeah, like it's a causal. Yeah. No, the amount of like furniture that you replace with French blocks is directly. It was like clearly in there. It's stupid. I think there's kind of two lines. Oh, let's turn on one side. Let's get on my level.
Okay, are there any questions before we get started? Coming to the end of module 2 next Friday. Next Friday, you'll get a performance stack. Aware of the schedule. How many of you are not aware of the schedule? Everybody, you're not. Okay, so you get the performance the next Friday. So let's take the roll call. I forgot to put on the mic.
When will the final exam be? Like the third module?
Yeah, very much like the first module.
Do you know when the third one will be? Like what day?
It's on the schedule. It will be after the 15th week. Okay, we have a 5-week module each.
This is what we've done like rainbow. It's just a boundary of the water, so it all is just surrounded by green. There is. It's a big one of metal, but it's actually a great big one. Silicon. It's almost real. Yeah. That's why the owner is shut off. Yeah, it's all sounds right. As we know. Exactly. That's why it shows up as a word. Yes. And the insults are so stupid, they're just bouncing around.
Okay, let's have a roll call. Elena Athanasiou, Muna Avajan, Salih Basama, Shankar, Colin Brown, Yu Hen Chen, Travis Crawford, David Zubon, David won't be here today. How happens? Dong Hu, Jarvin, Thomas Canal, Christopher Latham, Yu Ting Lee, Geoffrey Monte Sanchez, Mira Marinova, Logan Malikan, Sophie Thompson Payne, Ryan Schneider, Kun Pan, Brendan Triplett, Hao Chen Wang, Jie Wang, Yua Hua Wu, Ge Yang, Joseph Zulo. So let's get started today, continuing with the lectures on waveguide. Today I'm going to talk about a magic mode. This magic mode is called magic mode because it has very low loss. Okay, so imagine a cylindrical waveguide, circular waveguide. I mean, imagine that there's a wall here as well. The electric field is mainly in the phi direction. Okay, so you can imagine that the electric field goes around the waveguide very much like what we show here. Okay, electric field looks something like this in the circular waveguide. And this wave bounces around with the Bessel function, which is the J0, K rho rho kind of thing. So it would be n is equal to 0, so it's actually symmetric. Okay, there's something special about this waveguide. Imagine that if the electric field is pointing out of the paper in this manner, then the magnetic field has to point orthogonal to the electric field, and it will look something like this. You can go through Maxwell's equation and show that the magnetic field actually points like that. And if you have a bouncing wave picture of this mode, as the frequency goes up, this wave is going to get more and more paraxial. Okay, because you have to have the phase matching condition. Beta Z is equal to beta square minus beta S square. In this case, beta S is equal to K rho. Okay, or sometimes we call it K sub S. Okay, so as the frequency goes up, the wave vector is going to be more paraxial because this is a constant in the mode in the waveguide, because that is an eigenvalue problem. Because when we solve a waveguide problem, finally we reduce it to solving, for instance, for this particular mode
So this is an eigenvalue. And I like to point out the fact that this problem is an eigenvalue problem because it very much is homomorphic to this equation. You think of this as the eigenvalue is as the matrix operator A, and then this is the eigenvector. But the two problems are actually homomorphic to each other, except that in a partial differential equation, when you solve it, you have to impose a boundary condition. Whereas when you solve a matrix equation, you never talk about a boundary condition. So this eigenvalue is going to stay constant no matter what. It does not depend on the frequency at all. So as you increase the frequency, beta s is going to be a constant, and beta square becomes bigger and beta z becomes bigger. So the wave becomes more and more paraxial, as we said before. So when the wave is very paraxial, the magnetic field is going to be pointing more and more vertically. Can you see that? As the magnetic field becomes more and more vertically, it has a smaller tangential component. It's becoming vanishingly small. Can you see that? The tangential component of this magnetic field becomes smaller and smaller. And what is the boundary condition of the waveguide law for tangential H field? That tangential H field has to be equal to something. What is that? It should be equal to n cross H on the PEC surface equals. Anybody? No, n cross E on the PEC surface equal to 0, but n cross H on the PEC surface is not equal to 0, and what produces? Tangential H field on the PEC surface is, yeah, very good. Surface current. Okay, so this will be proportional to the surface current. And what this says, what this physical picture is telling you is that the surface current is getting smaller and smaller as the frequency increases. And there's a kind of loss in a waveguide, which is called the copper loss or conductive loss, because J ultimately has to be proportional to sigma E in the conductive medium. Sigma is not infinitely large here because we don't have a perfect electric conductor. So E is finite instead of being 0. And this J equals sigma E gives rise to what we call ohmic law or resistive law, very much like Ohm's law. Okay, so the fact that we have an electric field that is non-zero driving the current, some energy is lost to this resistive loss. So you can see that for this particular mode, as the frequency gets higher, the ohmic loss becomes smaller and smaller, and you see that. Physically, it is that tangential H field gets smaller. The current on the surface of this waveguide gets smaller. Because of that, the sigma E gets smaller. And hence the ohmic loss, I squared R, what we call the I squared R loss in electrical engineering, because if you go through Poynting's theorem, if you were to compute this using Poynting's theorem, this ultimately is going to be proportional to sigma E squared. And if you convert this to circuit theory, this is V over R loss, I suppose. If you have a resistor, the loss is V squared over R. Right? So this is the kind of I squared R loss. If you look at it from the current viewpoint, it's I squared R. If you look at it from the electric field viewpoint, it's V squared over R. This loss gets smaller and smaller as you increase the frequency. So I went through the physical arguments to convince you that this is true. And if you actually go out to solve this problem exactly, using all the mathematics knowledge that you have, and then you plot the ohmic laws of the sampling of this waveguide, you find that it's actually diminishes. That's the frequency increases. This is for the TE01 mode. For TE02 mode, the same thing happens. The loss tends to be higher. And the loss tends to be higher close to cutoff. The close to cutoff, remember, at cutoff, what happens to the bouncing rate? So to bounce, if I have the picture of a bouncing rate in the waveguide, what is peculiar about it? Bouncing rate bounces horizontally, or does it bounce vertically? What kind of it bounces vertically, right? Like if you have two parallel plates, if the wave is close to cutoff, then the wave is bouncing vertically. It doesn't move anything forward. But if it's above cutoff, then the wave starts to become direct. So you can see that the loss goes up. The loss goes up because tangential H is getting bigger, and also current, and then there will be more ohmic loss. So you can understand this picture in frequency without having to solve for the equation. And hence, if you have a circular waveguide, we like to have this magic mode in the waveguide to reduce the loss. For instance, there are two ways to reduce the loss by encouraging this magic mode. One is to use what we call a mode filter. A mode filter is what you have in the top right picture over there. They have radial spokes. In the radial spokes will short out the radial electric field. But this mode has no radial electric field. Look at the bottom, the electric field is purely circumferential. Okay, so the bicycle spokes that we put in the waveguide does not harm this mode at all, does not short it out. So the mode filter will encourage the propagation of the TE01 mode. Another way you can encourage its propagation is to use a corrugated waveguide. And if I go to the thought processes of this waveguide again, are the electric current on this waveguide circumferential or longitudinal? So you can go back to this picture again. And looking at this picture, and then you have the magnetic field and then the electric field. And if you imagine now how the current will flow on the wall of this waveguide. So this is circumferential or longitudinal. So what you do here then is to look at the H field. Tangential H will be proportional to the current. And if you look at this H field, how would the current on the wall of this waveguide be like? Anybody? Mira, you want to try? Okay. How will the current flow on the surface of this waveguide? If I look at this picture, E is something like this, and then H would be a curl of E, and not draw it very easily, but roughly it looks something like that. And if the H field is something like that, how will the current flow? So it's very good out of the case, and since it's a circular waveguide, it flows in the circumferential direction. Okay. So it flows in the circumferential direction, meaning that if I were to add corrugation to the waveguide, it will hamper the flow of azimuthal current. And hence it will not hamper the current coming from this mode. This mode has current. So if I make a corrugated waveguide, it will encourage the propagation of this mode. While the hamper the propagation of the other mode. So that's what people usually do in engineering. We do microwave engineering. You make a horn antenna which is corrugated, And that horn antenna would encourage the propagation. 0, 1. And then the field that comes out will be actually symmetrical over there. Because this mode has very low loss, it is also great for reducing the noise in the circuit. How many of you are familiar with the fact that if a circuit has loss, the noise is higher? How many of you know this fact? Okay, good. Many of you know this fact. Okay, that follows from the actually very early days was the Johnson matrix mode. That's your electrical engineer circuit many years ago. They found that the noise in the electrical circuit are related to the noise in the circuit for the Johnson matrix mode. And then later on, it got formulated into what is called the fluctuation dissipation field. The noise in the background of any circuit is proportional to the loss of the circuit. So it's a very big name of fluctuation dissipation theorem. And then if you have a very low loss waveform, it's great for radio astronomy. That in radio astronomy you need to detect very, very good signals from outer space. So there's a program for that. For example now, there's extraterrestrial intelligence. Search for extraterrestrial intelligence and radio astronomy, do things like that. But of course, that was not the only thing they do. They also look at galaxies in the outer world. They look for signals from galaxies. There are lots of radio signals from galaxies. We learn that anything that is hot, inside the radiation with a microwave in nature. Because it gives rise to all kinds of radiation, microwave radiation in one of it can detect those microwave radiation with the radio astronomy. Any questions? If not, let's move on to what is called a quasi-TEM mode in a waveguide. You already learned one thing, that if you have a coaxial cable, you can have a TEM mode. If you have a hollow waveguide without a central conductor, you cannot have a TEM mode. Okay? So you need a central conductor to have a TEM mode. You can have a TM mode in this structure. Okay. In general, if you have two conductors, you can have a TM mode. The magnetic field will look something like this. The electric field will look something like this. Okay. This is still TM in the state of power transmission line. But you can easily show that you cannot have a TM mode on this kind of structure. The only kind of mode that you can have in this structure are called quasi-TEM. Why? Well, let me try to convince you that when we have a TEM mode, the phase velocity of that mode has to be the phase velocity of the background. We already saw this in the plane wave. If we have a plane wave, it can be written as such. There's a plane wave, and there's a wave that propagates with the k vector or the beta vector in that direction. And then the electric field is orthogonal to the beta vector, and then the H field is also orthogonal to that beta vector. So if you were to make this wave TEM and make this wave propagating in the beta direction, you can see that if I were to get rid of beta X and beta Y by choosing a coordinate system that has only beta Z. So you can see that this mode has only the phase velocity of the medium in which the mode is in. Okay. And you can also show by mathematics that if you have a waveguide, it's part of your homework problem, which is that if I have a waveguide I can have a TE mode inside. Okay, I can have a TE mode inside. And then EZ equal to 0, but HZ is not equal to 0. And this mode bounces around in this manner. So it might propagate with a certain wave number in the Z direction. However, the moment I make HZ equal to 0, it will mean that beta Z will tend to beta I, where beta I is the wave number of the background medium. A mode which is TEM can have phase velocity which is that of the background medium. And you can show this in the homework. I have argued the case for same wave. We're seeing this in the coaxial cable. The coaxial cable, the wave that you have is entirely of this nature. Okay. I think you also did that one of the homework. So if a wave is purely TEM, it has to propagate with the phase velocity of the background medium. I can use the proof by contradiction, which in Latin is called reductio ad absurdum. So let me assume that I have a mode being guided along this waveguide. And let's assume that in the air region is TEM. Then in the air region, it will propagate with this phase velocity or this wave number. And if this is also TEM in the substrate region, this is usually called substrate or dielectric layer. It will propagate with a phase velocity of beta 1z. If both of them are TEM. What do you see the problem here? Two waves, one propagating in the air region with e to the j beta z, and in the substrate region we propagate with a phase velocity of e to the minus j beta 1z. What contradiction do you see here? Yes. Very good. Phase matching is not satisfied. So if such a wave that is always TEM in both regions, that is not possible. So when you have a structure like this, it has to be quasi-TEM, approximately TEM, but not pure TEM. Similarly, this structure too, you will have a quasi-TEM, and optical fiber too. Optical fiber is not a coax. You might have two regions, a core region with epsilon 1 here, epsilon 2 here, and then you might have air outside. And because of this difference in phase velocity, the three different regions, phase matching is not possible for TEM. And we'll go into greater detail in this problem. You will find that actually this problem has to be solved using what we call the hybrid mode. Yeah, we don't have much time to talk about the hybrid mode, but I can heuristically tell you what it is. So for instance, in the optical fiber case, you might have a core, you might have a cladding. In order to satisfy the boundary condition, the wave that you assume in the homogeneous region is TE and TM. Okay, you will have to have TE and TM here. Since you cannot have a pure TM wave, because of that, you have to have both HZ and EC not zero. HZ and EC not zero in general. Okay, you cannot set both of them to zero or one of them to zero. If you do set one of them to zero, you will have a TE wave, and you need to have both of them present in order to match the boundary to find that there's only one of the two waves. There are not enough equations to match boundary. That's why we have what we call hybrid form. In optical fiber, this is usually called HE or EH mode because they have both HZ and EZ not equal to 0. Sometimes it's EZ, not equal to 0. You have this kind of oddity. And we not, of course, do this in this course, but just tell you about it so that you can read about it if you want to. Any questions so far about this hybrid mode in an optical fiber or a dielectric waveguide in general? For the case of a slack dielectric waveguide, we are lucky. We are lucky that there we can have both TE and TM, and we can decompose the wave into pure TE or pure TM. And we solve the problem very simply without the need for a hybrid mode. Similarly, in the optical fiber, you can also make the problem symmetric so that you can have a TE mode only or TM mode only, but those modes are not interested for optical fiber because they're not the most important modes in optical fiber. The important modes are the hybrid mode, HE and EH mode, and those modes, one of them does not have a cutoff. And that is the dominant mode in the optical fiber. That dominant mode is called the HE11 mode. And this mode has no cutoff. Okay, I will not go through the mathematics, but if you have any questions about this mode, let me know. I can answer them in a heuristic way. Okay, any questions? If not, then we just let the reading be done by you. Okay, you can read up the waveguide theory course lecture notes, how the net boundary conditions. Those are usually very easy. So let's talk about yeah, this is I just finished that. Okay, hybrid modes and homogeneously filled waveguide. So the next thing I like to do is actually use homomorphism between waveguide and transmission line as much as possible, so that when we have a complicated waveguide problem, we can count upon our knowledge in a transmission line. Okay, to solve a complicated waveguide problem. How do we do that? Well, it turns out that this can be done. It turns out that in a hollow waveguide, for instance, we know that there are two kinds of modes, TE or TM. And this decomposition is quite clean. We either find a pure TE mode inside the waveguide or pure TM mode inside the waveguide. So let's start with the TE case and see if we have a general TE mode propagating in this waveguide that has homomorphism with the transmission line theory. So that we can do a one-to-one matching of this problem into a simpler problem, and we use a simpler problem as a clutch to hold ourselves up. EZ is equal to 0. Z is not equal to 0 for this TE mode. And of course, you know that you can start with Maxwell's equation. You have Ampere's law without the fourth term. Okay, we assume that Ampere's law with no fourth term. And then we decompose our del operator into the transverse part plus the longitudinal part, where the transverse part is just partial x plus y partial y, and then the longitudinal part is just this part. Okay, so this is quite straightforward, nothing very profound. The next thing that we need to do is to strictly ignore the waves or the fields into transverse and longitudinal again. And if you do that, then you will let H be equal to HS plus HZ. And we do the same thing for E. So the ES plus EC. Okay. So if you do that, then you can go through some tedious algebra. And rewrite Maxwell's equations as this. Left-hand side of Ampere's law is equal to that. And the next thing we do is to expand this thing. So if you expand this out, you get 4 terms. You get 4 terms, but one of the 4 terms is 0. So which of the 4 terms is 0? Just to make sure they will not do it. Very good. The last one is 0. I think you write it in all the detail. We had cross, and that will go to 0. So very good. So the last one goes to 0. So we have a simple equation to work with. So we make a small gain here, and then the next thing we do is to actually equate this to the right-hand side, which again can be broken into E sub s plus E sub t. So of the 3 terms on the left-hand side, which one points in the z direction and which one points in the longitudinal direction? Okay, so I know that the right-hand side has a component that is transverse and a component that is longitudinal. So let me match the transverse components first and see what on the left-hand side we should pick up in order to match this transverse component. With the first component here be transverse, you take a transverse component crossing with the transverse component with the good in that will be very good. So the first term can be thrown out and we try to make it. And then the second term, the D term crossing with the F term, which is the transverse term. And then the third term, so I can easily simplify this equation by matching components and say that this should be equal to okay. And then I have a simplified equation sort of, but my goal in doing this is one thing. My goal is to see if we can manipulate Maxwell's equations to look like the telegrapher's equation. And bingo, I'm done. I know that if I can map my Maxwell's equations into the telegrapher's equation, then I can actually solve my problem. Okay. So our goal is to do that, and we haven't mobilized all of Maxwell's equations yet. We only have used Ampere's law. So the next thing, of course, we do is to look at Faraday's law. So with Faraday's law, I can do that on the next slide. I start with curl of E being equal to minus j omega mu h, Faraday's law in the frequency domain. Again, I expand this out in 4 terms, but only 3 of the 4 terms are important. So this is the truth. Faraday's law becomes just true. Next component by component, left-hand side, right-hand side. So I just put S back to here. That doesn't look like a Z. It should be a Z. Okay. So if I match component by component, then I know that this one must be pointing in the z direction. This must be prudent. And then this other one, okay, this is a way to move forward. We have found this equation, and it doesn't look like a calligrapher's equation yet, because it involves both hz and hs on the left-hand side and es on the right-hand side. And now if I look at this equation, I find a connection between hz and es. Okay, so there's a chance for me to eliminate hz from this equation. If you look at this equation on the left-hand side, I have a chance to eliminate hz from here using this equation. Okay. So if I do that, then this equation from the previous slide can be written as cross hs so as cross 1 over j omega mu, so as cross es, which is I had make use of this equation, okay, to rewrite that term in this manner. And then the right hand side will be j omega epsilon e sub s. Okay. What I've done is to look at the previous slide. Look at the equation I had previously, which is this equation. I get rid of this hc, and then we get rid of this hz and write it as es. I have an equation relating es and hs. That makes it closer to looking like a calligrapher's equation. The next thing I need to do then is to manipulate this equation further to make it look more like a calligrapher's equation. So I have to simplify this double curl. Okay, and all of you know how to simplify a double curl operator. So when you see a double curl operator, which formula do you use again? Back to the cat formula. A good location to use the back of the cat formula. And if you do that, then you will show that this is actually minus. Okay. But what is the transverse divergence of E sub s? Well, I like to convince you that it is zero because there's no source in the waveguide. There's no source in the waveguide. Everything is homogeneous. First, I like to convince you that divergence of E equal to zero in the waveguide. But we're looking at TE modes. Remember, we started out with looking at the TE modes in this waveguide. Okay. So what it tells us is that E is only ES only. EZ equal to zero. Agree? So if divergence of E equal to zero, this is also equal to zero. Can you see that? If the divergence of E equal to zero, and if this way is TE and there's no force on the waveguide, transverse divergence is also equal to zero. So that is wonderful. We just have to throw this out. And this would be just the transverse Laplacian of E sub s. Okay. So there's one more thing that we can say. Well, we have previously shown that in a hollow waveguide, this is true. This is true in a hollow waveguide. Do you want me to prove this or content with just saying right? You can derive this equation anytime. So start off with Maxwell's equation to eliminate the E from the two Maxwell's equations, then you get the Helmholtz equation. And this equation is true for all three components of the electric field inside the hollow wave side. Okay. So, but this can also be written as transverse Laplacian plus but E can be written as E equal to ES for TE mode. Okay. So, but what is partial square, partial Z square? Partial square, partial Z square becomes minus something, right? What is that? It should become. For a waveguide mode, partial square, partial Z square should become. Beta, yeah, not B, beta. Beta Z square. Okay. So if that is the case, then this equation simplifies the transverse Laplacian plus beta square minus beta Z square E sub S equals to 0. And this is just beta square minus beta Z square is what? It's the eigenvalue of the waveguide problem. Okay. This is just equal to that. So we got the fact that the transverse Laplacian plus the waveguide eigenvalue should be equal to 0. So we can use that to simplify this. Okay, the double curl operator looks awful. It is equal to the Laplacian operator in 2 dimensions, but then using this, we can eliminate this. So this double curl operator can be simplified. And if you do the simplification, you end up with an equation that looks almost like the calligraphic equation. Let me see if I have it written somewhere. Okay. So what you have is that this double curl operator simplifies. Yes, my thesis here simplifies to something like this, and then this just becomes beta S square. Okay, this is just beta S square. Something like that. And then you can move this term that involves only E sub S to the right-hand side and group it together with the E sub S on the right-hand side. And the equation that you have after that manipulation is this equation over here. This equation over here. I'm not going through the details, but you believe me, this is what you get. And you can combine this to be beta square minus beta S square is beta Z square over beta square. After you make use of the fact that beta square minus beta S square is beta Z square. Can everybody see that? So the Ampere's law becomes very simple. And the whole is like almost like this calligraphic equation. And you can combine the beta square with beta S square to making the beta Z square. After you bring them under the same denominator. Can everybody see that? How you can see that? Good, very good. At least some of you are seeing it. Okay, so we have one of this equation, and then of course we have to look for the other telegraphic equation. That comes from this other equation that we are looking at. It must come from Faraday's law, right? We were looking at Faraday's law just now. We were equating this. We get one of these equations to eliminate C, but we did not make use of any of this yet. Okay, but for the TE mode, this is equal to 0. And then this must be pointing in the transverse direction. So we can extract one more equation from Faraday's law, which is the second equation that would be important for us to form the calligrapher's equation. So if you look at the other equation, if I write it out properly, it would be something like so Z cross E sub F equal to plus J omega, maybe with a minus sign. I'm always having problem with minus sign. Okay. So if you look at this pair of equations and think of your grad Z as being Z hat partial Z. In tandem, they look like calligraphic equation. Partial Z on the left hand side, and then something that looks like the voltage on the left hand side. Pairwise fashion, they form this calligraphic equation, and you just have to do the proper mapping. The E sub S maps to voltage, V cross H of S maps to current, and then mu maps to the line inductance, and then epsilon, this factor here, okay, which is epsilon beta Z square over beta square, which can be written as epsilon cosine square theta, theta being the angle of the wave that makes with the Z axis, and this can map to the line capacity. And then you can also derive the characteristic impedance, which is L over C, and in this case will be the wave impedance of the waveguide. Okay. And then repeat for TMK. So what I have convinced you, hopefully, is that if you have a waveguide, if you have TE mode or TM mode in a waveguide, then it is for TEK. You can be mapped to the calligraphic equation, even though it looks very complicated. The waveguide can be of any shape, but that problem can be mapped into the calligraphic equation. You can repeat for the TM case, you will find that there is also a pair of calligraphic equations that can map to it. So both of these problems can be mapped to TE and TM mode. So what I'm saying is that if you have a waveguide problem, you can divide it into many sections. Each of these sections can be mapped. Problem. Yeah, the calligraphic equation. And hence you can solve this problem. Irrespective of how many sections you have, you can complete one field. Is that fair? Okay, I see Travis more in the case, so Travis and Cornell, right? Did they get your name right? Thomas Cornell. Yeah. I see we both one in the head. So you're getting it. Okay. So things are not that simple in the real world. This is a very idealized case. Idealized case in the sense that we have the same waveguide, and the reflection of the waveguide doesn't change. So if we were to propagate a single mode in this waveguide, we will retain the shape of the waveguide or the shape of the mode, and the mode will remain single mode as we propagate down the waveguide, just like a plane wave in free space, or plane wave in this layered medium. That problem we did before. We did the Fresnel reflection coefficient, we did transmission coefficient. You assume a plane wave in one region, and then you get a plane wave in the other region. But this problem is more complicated than the plane wave. If you assume a mode in one region, it remains a mode in the second region, the same mode in the third region. Okay. So you remember that the modes are found by solving this eigen equation. So this beta S does not depend on the medium at all. It is an eigenvalue that depends not on the medium but the shape of the waveguide. Depending on what waveguide shape you have a different eigenvalue possible. Well, life is not that simple. The real world is more complicated than that, and usually we have multi-junction waveguide that looks like this. Something new happens here that did not happen in the previous multi-junction waveguide. In the previous case, if you assume a mode propagating in one section, the same mode can propagate in the other section. Let's say it is TE10 mode, one section in the waveguide. It remains to be TE10 in the other section. Long as it propagates down the waveguide. So this waveguide is not possible. Because if you assume a TE10 mode coming in, say, section 1 of the waveguide, section 2 might have a TE10 mode, but the cross-section is sufficient, so you cannot make boundary conditions for the junction. So in order to make boundary conditions for the junction, you need multi-mode. So you need infinitely many modes in the 1-2 junction in order to make boundary conditions in the 2-2 junction. So you need multitude of modes, or infinitely many modes. So just one mode coming in will induce the occurrence of many modes. That is called mode conversion. That is very important in waveguide theory. So you have a new physical phenomenon which is mode conversion. A pure mode coming in, a section of the waveguide will induce the propagation of multi-modes in the other section, in order for the boundary conditions to be met. Does this make sense? I see a lot of nodding heads, so that makes sense, I presume. Okay. So the next remaining hours, I'd like to talk about Resonator. So how can we make the simplest resonator? The resonator is something that causes constructive interference of a wave. The simplest resonator that you have is that of the LC tank circuit. As an electrical engineer, you have studied this resonator before. And fortunately enough, in circuit theory, there's very little phase shift. You can think of this as being magnetic energy report into the capacitor conversion into electrical energy, and the electrical energy report back into the inductor converting that into electric energy, back and forth, the energy resonance between the two regions, and we have a resonance device, which is called the LC tank circuit. So in microwave engineering, you can do a lot better than that. You can define very many different kinds of resonators. And one of which is just taking a transmission line, terminated on the left with a source impedance, terminated on the right with the load impedance, and if the wave bounces back and forth, and if it interferes constructively, we have a resonant mode. What is the criterion for then the interference constructively? You have to bounce around and you have to be in phase, right? You have to be in phase, it's important to phase. And what is the other criterion that is needed in order to have a resonant mode? It cannot be lost in the system. If the wave bounces around and if there is dissipation lost in the system, the wave disappears, dissipates the wave. So in order for a resonant mode to exist, this wave bounces around, and then you have to sustain itself by constructive interference. And that is only possible if there's no loss in the system. And this kind of system you have studied before. It's very much like this layered medium problem, where we send in a wave. And we say that this wave would interfere constructively if I call this 0, 1, 2. Dielectric flat waveguide, we say that this would be R12, R10, e to the minus J2 beta 1C D, D being the length of this. And this being 0 implies constructive interference for the transfer part. You can use the same kind of thing. Just going down to second form, take away that you have constructive interference, and then you would have resonance. And these loads and the source loads better be lossless. And how can you have a lossless load? What in electrical engineering tells you that you have a lossless load? Yes, very likely. This is another way of this is that you have a pure reactive load. Okay, a pure reactive load. And if you have a purely reactive load, then those loads are lossless. They only store energy, they don't dissipate energy. So you can make transmission lines into resonators quite easily. Then, as I said before, you terminate two ends of the transmission line with reactive elements, or you can also take the microstrip line. For instance, the simplest way to make a transmission line is use microstrip line. You know what that is. What you do is that you have a ground plane below, and then you have a microstrip line. And the microstrip line, together with the ground plane, makes something that looks like a coax. Not precisely coax, but looking like a coax. And this microstrip line has a pure TEM mode. Does it have a pure TEM? No, actually, just learn that. Okay. So that you're not using. So this microstrip line, together with the ground plane, does not support the pure TEM mode. So it supports the quasi-TEM mode. But you can still imagine this, the wave going back and forth at this point using your lump element model. Let's see how it will get extension energy in this microstrip line of the electrical energy source to magnetic energy source. And the way this propagates down the line, like in the lump element model. And then it will bounce around back and forth. You can make it into a microwave resonator. Then you can also take a waveguide, for instance, a rectangular waveguide, terminate it. Okay, this is a rect waveguide. And then you can either short circuit the waveguide at both ends, cause perfect reflection, or you can open them. And if you open the waveguide end, you have a lossless waveguide end. So you know that in transmission line, it's quite easy to think that if they have reactive elements terminating in transmission line, there will be no loss. The wave propagates to the end of the transmission line. What happens if I have an open waveguide? I let it be open. Let the waveguide mode propagate to the end of the waveguide. What happens at the end of the waveguide? Yes, it was reflected. There's one thing that happens. What else happens at the end of the waveguide? Well, if you can't think, let you think this way. Okay, let's think of a parallel plate waveguide, and you will have a guided mode in this thing. And let's think of the other waveguide as being a very large parallel plate waveguide. What happens to the other side of this waveguide? Will it have more modes or less modes than the other waveguide you start out with? And to make the waveguide bigger and bigger, the number of possibilities is large. There will be more and more modes on the other side. So what happens is that if you just start out with one mode, as we said before, you need mode conversion to match boundary conditions. So this mode will spill into infinitely many possible modes on the other side. And now if you think of the right-hand side as an open waveguide, then this mode becomes plane wave, infinitely many plane waves propagating in this direction. And they will propagate to infinity, never to be found. What do you call that? There is a radiation, or you have radiation loss. So the mode will go to the other end, mode converts to plane wave that goes to infinity and never having a chance of coming back. So it doesn't want to be bounded and back. All right, so it's 8 4. Maybe I will throw the ball back to you. But here the ball goes to infinity and never comes back. Okay, the radiation loss. So if you have an open waveguide with open ends at the both ends, you have radiation losses. And then the reflection will not be perfect. Okay. And the same thing you can do with the circular waveguide, for instance. The wave goes back and forth, but at the other end, it will start to radiate unless you terminate with a perfect electric conductor. Then the wave will be completely bound back. Okay. So resonators are very important. One of the most important one is actually a quarter wave resonator, which is used a lot in cell phones. Say if I open circuit this transmission line at one side and short circuit it on the other side, what is the mode with the lowest resonance frequency on this transmission line? It actually is a quarter wave, because on the open side, the voltage will be maximum or the current will be 0. On the shorter side, the current will be maximum and the voltage will be 0. So either way, if you plot the voltage, will look something like this for the resonant mode. And then for the current, this is the voltage, this is current has to look something like this. So either one you look at, they are forming only a quarter of the waveform. So this resonator can be made to resonate at a quarter of the waveform. So if you say take 10 gigahertz, wavelength is 2 centimeters. The quarter of that wavelength is very small. You can make a small resonator for the transmission line. So quarter wave resonators are very popular in cell phones. So those antennas that you have in your cell phone are probably very small. So I'm going to use a lot of heuristics to talk about this part of the course because you understood the physics and the math for some flow solutions. Most of the problems in this course do not have flow solutions. So we try to use the total solutions to understand complicated problems. So if I have a transmission line, such as this one, a coaxial cable, and I want to make it a resonation. The simple thing I can do is to open circuit one side and then short circuit to the other side. And if I open circuit on the right hand side, do I have the two open circuits? Because it's really very easy to make an open circuit at this point along the current. But in electrodynamics, it's not possible. Why is that not possible? Because on the right hand side, we terminate in this manner, and as the current flows, the current, as we say, will be maximum on the other side, and then it will be minimum on the right hand side. Okay, J is not constant. So if J is not a constant on the transmission line, what kind of field is conserved in your mind for non-constant case. Non-constant current. Of course, in circuit theory, everything is constant. Current number one is constant. But in electrodynamics, problems are not constant. What is the first thing that comes to your mind when you have a non-constant current? Magnetic field not true. That is true in a sense, but magnetic field is electric current of nature. But when the current is not constant, what do you think of? Okay, when current is not constant, the thing that we have to remember very well is the continuity equation. So what does this equation say? If current is not a constant, divergence must not be zero. So if divergence of the current on this transmission line is not zero, what must happen on this transmission line? Charge accumulation is very good. The charge cannot be zero on this transmission line. So if you were to plot the current to be this way, the charge will not be zero. The charge actually gets to be zero on the left hand side because this is like the time curve. But close to the other end, the relative of the current is not zero, and we have charges at this point. In fact, you will expect to see lots of charges here, maybe more of them accumulating on this side, but less of them on the left-hand side. And when you have charges on the right-hand side accumulating, what happens? You have an outer conductor which is positively charged. The center conductor must be negatively charged or passing charge. You always have the coaxial cable, the current is on the outside, but inside the current is going opposite direction. So if on the outside the current charges to the end of the transmission line on the outside, and the inside it must be fixed to charge. So you expect the electric field to look something like this. Agree? There'll be negative charges. Electric field will look something like this. Okay? So these are called fringing fields. It can never become a redox in electrodynamics. The divergence of phase is never equal to zero. Only in Kirchhoff current law, there is divergence of phase equal to zero, but it's circuit theory. So you will see this kind of effect happening, giving rise to what we call a fringing field capacitance. And the proper model for the transmission line is the one in the bottom. So you can make resonators quite easily by terminating a transmission line that way. You can also make resonators quite easily by terminating a rectangular waveguide at two ends with short so that there are no radiation losses. And then the wave will just bounce back and forth. So imagine that you have a waveguide, there was a mode in the waveguide, terminate the waveguide, the wave just bounce back and forth. Like what happens in the transmission line. So you solve this problem as a boundary value problem, which you should be very good at this point. And then look for the mode. And you probably have seen this solution before, okay? That in the rectangular cavity, that beta square previously was beta x squared plus beta y squared plus beta z squared for a plane wave. We have a bouncing wave. And in the waveguide, we have beta squared is equal to n pi over a squared plus n pi over b squared plus beta z. This is waveguide. But in the cavity, because the wave is bouncing back and forth in the z direction, we have one additional discretization or quantization. Some people like to call it that way, but it's not actually quantum theory. Okay, the cavity, the wave bounces around. In order for them to exist in the wave cavity, this condition has to be satisfied. Either G has to be integral multiple or pi over D. You want me to derive this or is it okay? I think most of you have seen the ascending wave on the 1D line. This adds the understanding of 1D physics to a rectangular wave that you get the last equation. Okay. And if you go through the analysis very carefully, which I wouldn't do, the electromagnetic field inside the cavity will look something like this. And the one with the lowest resonance mode is called the TM110 mode. Okay. What you do then is to look at this equation, stare at it enough. And if D is a very small number, then you make M equal to 1, N equal to 1, T equal to 0, you get the lowest mode. Okay. And you can repeat the same for circular waveguide. You terminate at its top and the bottom by the PEC plane, and then you can have a resonator. Of course, in the real world, you won't play with simple things like terminating a wave in a simple fashion. You will take a waveguide and terminate it in this manner, make it into a radiating antenna. And if the electromagnetic field in the cavity is made to resonate, the field inside the cavity will be strong. Does this concept look familiar to you or something? If you go to the top and play with the swing, if you know how to pump a swing, if you did when you were a kid, I guess maybe you are too old to remember it now. You know how to pump a swing. If you pump the swing at the right frequency, the amplitude of the swing will become bigger and bigger. Similar physics happens here. If you were to pump the cavity with the correct resonance frequency, the electromagnetic field inside the cavity becomes bigger and bigger. And so with the accompanying electric field at the aperture of this antenna will start to radiate and become a better and better radiator. And that's how you can use cavity to enhance the radiation of a thing, and then you can make a lot of fancy things. Like microstrip lines, you can connect them together. They can make coupled resonators. And here's an example of a coupled resonator using microstrip line. The picture on the left, on the top, is like an astral thing. You have to look at it there. At the top and out and see a different picture. Can you see that? You can either imagine that checkerboard thing to be the top of the table, or you can imagine to be the ceiling of the room. Okay. Just put my card as the ceiling. Now you can see at the top of the table, right? So this is just design of microstrip line. So it's not a very nice picture. I took it out of MATLAB. Okay, not very good. And you can make this into a filter. Okay, you can make this into a filter. When things resonate, then it's very easy for the wave to go through. When things don't resonate, it's very hard for the wave to go through. You can make Fabry-Perot resonators in optics as well. You can make the flat resonate with a certain optical frequency, then you can make a filter. And similarly, you can make microwave forces. This is an example of a microwave force where you have a klystron. And the klystrons are supposed to be resonators. You put in microwave energy into one of the cavities and you send a beam of electrons outside through that resonator. And the electron has kinetic energy, and that kinetic energy will be converted into microwave energy. That goes through the first cavity, making the energy stronger and stronger. Okay? And then that cavity energy is transferred to the passive cavity, giving you a way of generating microwave forces. And you can make lasers. Lasers are also made out of cavity. So what you have is that you have an amplifying medium. I'm sure that a lot of you are from the optics area, you know how to make this into an active medium so that when you send these waves bouncing back and forth, they get amplified by that structure over there. And you can also make what is called a room temperature semiconductor laser. This is a Nobel Prize winning project. Because for a long time, people couldn't figure out how to make. I'm not supposed to go again. People couldn't figure out how to make something late at room temperature. Then they make this into wave and get the electromagnetic energy to be confined inside this wavelet. And at the same time, they produce a lot of electron hole pairs to generate the energy needed for laser. Okay. So this work brings about Nobel Prize to 2 people. And then, of course, you can also use cavities to measure resonant frequency of the cavity. I'll write down more about it in the lecture notes. You can read about this kind of thing. And so there are plenty of applications for cavity, lasers, amplifiers, and all kinds of things. Cavities are quite important in engineering. Yeah, I'll stop here unless you have any questions. No? Good. Yes. Yes.
So, can you explain the part about microwave that they use in the transmission line picture? The transmission lines are still, you're using the homomorphism.
Right. The mathematical homomorphism.
But physically, this is an entirely different thing.
Right.
So when you explain the distance of fringe capacity, right, using the transmission line model, right? So in an actual physical system, there will be a fringe capacitance, right? But it would be equivalent to that which you get from the transmission line model.
Right.
So I was just confused because the fringe capacitance is a physical thing,
Right.
in this system also,
Right.
the actual system. But in the transmission line, so in an actual microwave cavity, it looks nothing like a transmission line.
No, not at all. Yeah, the transmission line model was a simple model to explain the fringing field capacitance. But in a rectangular waveguide, if you were to open it, there will also be fringing field.
Just because of the not equal to
J not equal to 0, and then the current is not uniform when the current flows to the edge of an open rectangular waveguide, there will be charges accumulating there.
But in the transmission line, you have the opposite current, and you could argue that it's like a capacitor because of the opposite charges.
Yeah, but then in the rectangular waveguide, you can see that the top plate and the bottom plate with charges of opposite sign. So the fringing field, instead of going from the outer conductor to the inner conductor, as in the case of a coaxial cable, will be going from the top plate to the bottom plate, or the other plate. So it will produce some kind of a fringing field capacity, but not so easy to model as in the transmission line. Okay, but the same kind of physics is there. Okay.
And the other thing was I remember we defined this cutoff frequency in the previous lecture. So does that carry over to the resonator system also? Is there
Cutoff frequency is a tricky thing. For a dielectric waveguide, cutoff means that the wave is not cut anymore. When the wave ceases to be evanescent outside, we call that cutoff. But in the rectangular waveguide, we say the mode is cut off when it becomes evanescent in the z direction. Okay, so the two definitions are quite different. Cut off for dielectric waveguide and cut off for cavity resonators and so on. Okay, they're quite different. Okay. Yeah. Okay.
You have a class here? Oh, okay. Only on Thursday?
Yeah,
Or is it booked?
I think it's both. Well, on my schedule, on the weekend, a client's going to Okay.
Well, because I booked this room on Tuesday after class.